Hello, everyone. I'm talking about pumps today in this class. Um, Again, it's greenhouse technical, so don't be surprised if there's some numbers and graphs in this. And once again, don't be surprised if this is something that you will find useful in the field of horticulture. So I want to introduce you to the various types of pumps that exist in greenhouses. Also, basically the same applies to landscaping, although primarily nursery production as well as greenhouse. So let's go over some basics. Um, Pretty straightforward. We have high pressure pumps and we have high volume pumps. It's almost always very difficult to have both, right? So it's high pressure or high volume. Um, Think of like a pressure washer to clean your car. It's got high pressure, but it's not shooting out a fire hose. It's a very thin stream that's high pressure. So usually these two kind of come in opposite relationships. So part of this lesson, actually a big part of it, is trying to figure out what's the right pump for the application. And so right off the bat, there's something for you to feed into your decision. Some basics. I want to talk about units. Uh, Today, unfortunately, I'm still using a lot of imperial because I find a lot of graph and pump data is still in imperial units. So let's talk about PSI. You can, of course, get kilopascals, which is the metric. You can also convert them. Google will happily do that for you. Um, Same thing here. GPM is gallons per minute versus liters per minute. I tried to use a graph in the slideshow today that uses both metric and imperial, if that helps. But then a couple other terms I'm going to elaborate on soon. One is the head pressure of the pump and the lift. So let's talk about those two. Um, the X here, this part here, represents the pump, okay? And here we have an example of where the water is being sucked from a cistern below the ground, or that could be a pond if it was open, right? And then, of course, there's how far it has to lift. If it's a greenhouse, right, that could be gutter height, right? So how high is it to where your hanging baskets are, for example? That would determine the height that the pump has to push the water up. So that's what we call pump head. Pump lift is how far we have to lift the water up to get to the pump, okay? So there's head and there is lift. So if the pump is below liquids, then lift is really not so much of an effort. So for example, in a greenhouse, we often have these large tanks that store water, fresh water and then nutrient filled water, and the pump would be located down below. But that means it doesn't have to suck water up. It just means it's going to be primed quickly with water and it has to push it out, and maybe a little higher than the height of the tank. So this diagram will help you understand the relationship between lift and height or head pressure. So the pump is represented by this symbol right down here. And in this case, it's just circular. Right? So we have a tank and it's pulling out the bottom, pushing up to the top. Because the water level's above both, there is absolutely no resistance. The water will just as easily go into the pump as it will come out of the pump. So this is going to fling water around rapidly. Here we have a situation where the tank is above the pump, right? And we have a tank that is filling and the tank is still not full. So what is the ultimate head pressure? Well, we still have to go up to this high part. So that part here from here to here represents the difference, and that's our total head. Of course, as the tank begins to fill, it goes higher and our head increases. So when we're sizing pumps, we have to make sure we're looking at the extreme scenarios to make sure the pump will work in all conditions. Another term is deadhead. Now this has nothing to do with geraniums. What it means is that if you have a pump that's sucking up water and pushing water higher and higher and higher, eventually the pump can't push the water any higher and the water stops flowing. That is the dead head height. So here's a graph showing down here is the flow rate. This is gallons per minute. And as the height that we pump increases, you can see the flow starts to decrease until eventually the flow basically stops. And that is the maximum height that the pump can push water. So basically, this is where your pressure is equal to the pressure that the pump is able to, the downward force of the water is equal to the pressure of the pump that it's able to push up. So the water stops flowing. Okay, let's look at a pump selection scenario here. You've got 200 hanging baskets with drippers, right? Each dripper is emitting 1 gallon per hour. So it's 200 hanging baskets, 1 gallon per hour. You also have to water your benches in the morning, which has sprinklers, 24 overhead sprinklers per bench at 18 gallons per hour. Okay? You need 40 psi to operate your sprinklers. If there's not enough pressure, the sprinklers just dribble the water out. It doesn't fling it out, and you don't get good coverage. Another thing to keep in mind is how far is the pond below your pump. So you're pumping from a pond outside your greenhouse into the greenhouse. There goes my phone, as always. So there's the lift height of your pump, right? And then, of course, there's gutter height. That's where your hanging baskets could conceivably be, or maybe slightly below that. But we'll just say the height of the gutter. And that gives us our math for our lift height, and then we know how much water we're going to have to pump. Let's do the math. So 200 hanging baskets times 1 gallon per hour, that's 200 gallons per hour for hanging baskets. 24 times 18 gallons per hour for your sprinklers, that's 432 gallons per hour. Notice the sprinklers use a lot more water. I mean, drippers is just coming out slowly, so it's not too bad. The total volume, we add that up. We're just assuming one bench here. It works out to 632 gallons per hour. And if you do the math, we can convert that to minutes, divide by 60, and we get 10.5 gallons per minute. And there's our lift height of 15 feet. Our head height is 10 feet, and our pressure is 40 psi. So I have a graph that looks at different pumps. That, for example, at a company, you would look at these graphs if you're trying to make a selection, and you have to be able to read it to say, okay, which pump do I want to buy that's going to suit my needs? You don't just go out and buy a great big honking pump. You got to buy the right one. So we're looking at 10.5 gallons per minute, right? And that's this whole line up here, 10.5 gallons per minute. And this line here is our total head, which is 15 feet. Okay, so they cross right there. Look at this. It's sort of irrelevant with these graphs, but we're going to go up to the 10.5 gallons per hour, and we're hitting this line here. Okay. One other thing that the chart helps tell us here is that for every foot of head pressure, we have 0.43 psi. So if you look at this, it's 100 feet at that volume at 10.5 gallons per minute. We get 100 times 0.4, which is 43.3 psi, which means we just have enough pressure to run our sprinklers. Okay. If we wanted some insurance, we might want to move from the 7SN to the 10SN, right? That would push us up to here, which would give us around 58 psi, 55 psi. So let's take a little closer look. On the suction side, so these are the different same pumps on the last slide, 5SN, 7SN, that's the one we originally thought would be good. And then there's a 10SN. This is a 3/4 horsepower. This is a 1 horsepower. Now this is the pressures. This is sort of just giving you a range. So 30 psi, 40 psi, 50, 30, 40, 50. Now we said 40 was what we want to be able to run our sprinklers. So we have 5, 10, 15, 20, 25 suction lift for our pond. So we're in this category. Okay, we said we needed 10.5 gallons per minute. This is all in gallons per minute. So the 7SN with the suction of 15 feet, remember that slows the rate in addition to the lift, brings us down to 10.1 gallons per minute. Whereas the next size pump, the 10SN, puts us safely at 15.8 gallons per minute. So this pump seems to have a little extra capacity, nothing crazy, but this one's just a little bit too close for comfort for us to reliably know that that pump's going to do what we need. Which brings me to this next graph, which talks about pumps being in their most efficient range. We want to make sure our pump is not overworking or underworking. For example, if we went for the biggest possible pump, it might spin up, pressurize the line, and then shut off until the line depressurizes and then cycle again. And that means that the pump is always turning on and off and on and off, which is going to burn it out. So usually you try to size the pump within a certain range, about 85% of your capacity. Of 85% of the pump's maximum capacity is your sweet spot for the size you're going to get. And so that last pump we saw, which was at 10.1, was basically at 100%, where the next pump, which was 15, puts us at around 75%, which is okay. That's maybe a little bit big, but it's not like they've got an infinite selection of pumps. So we know which pump we need to buy. There it is, 10SN, this one here. That's the one we want to buy. All right, that's enough pump selection. Let's look at the different kinds of pumps. There's jet pumps in greenhouses. They tend to have an elongated nose in the front like this. They are useful for when you're lifting water that is further down than 15 feet. So they have a little more suction than most other pumps. That's why a lot of shallow well pumps use these types of pumps. A lot of ponds, suction from ponds, we use these. An important thing to remember about ponds, so let's say here's your pond, right? It's full of water. There we go. Full of water in the beginning of the summer. As the summer goes on, the pond gets lower, which means your suction height becomes deeper, right? So you should, again, plan for all scenarios when selecting pumps. This is a cross section of a jet pump. Kind of tricky to follow. The water comes in here from your well or pond and gets sent through the pump and then gets shot out the top to your irrigation stuff. What you'll notice is that some of the water can go around this casting and come out the bottom and actually recirculates through into this jet orifice and shoots around again, right? That some of the water exits and some recirculates. This jet part where the water shoots through this narrowing nozzle through here helps suck the water from the pond. That's why it's called a jet pump. This added velocity draws the water in. We call that a venturi. Here's a cross section of a venturi. So if I shoot water through here where the passage narrows, see how it gets narrow here? The speed, the velocity increases, which creates negative pressure, and that pulls the water up. So jet pumps are suitable for higher lifts. So we have to lift the water more than 15 feet below where you are. Okay. Next, the most common pump, which is the centrifugal pump. These pumps look like this typically. The head is not as long as a jet pump. It's a bit shorter, right? They are not as good at sucking, so they don't have the same kind of suction, which is fine for a lot of applications, provided you're not lifting more than 15 feet. A lot of irrigation pumps are like this. Typically, it's just an inlet and then an impeller that spins and flings the water out, and away you go. There's a link on this slide. I'm not going to click on it, but you can watch. It's a lot like the vortices on a tornado, right? So the tornado would be where your pond water comes in, and then the water flings out the side. Did you like that? Next, booster pumps. You may or may not run into these. Sometimes when you have a pump in the irrigation room, it has a long way to go to get to the far end of the greenhouse. And so they have these pumps along the way that have an inline switch where if the pressure drops, it will switch on and help boost the pressure again so that it has enough pressure when it gets to the far end of the greenhouse. So it's basically an assistant with this built-in switch. So if you see the pump with something like this, it's either a booster or it could be a temperature override switch. Those temperature switches are common because if you run dry, say you run out of water, Or worse yet, the pump doesn't shut off, but the water's not flowing. The water will get hot inside here and start to boil, and then that temperature will shut off the motor so you don't damage your pump. But oftentimes it's a flow switch. Diaphragm pumps, you may see these on sprayers. These are typically used in applications where you're dealing with chemicals that might attack your pump components, so you don't want to have it in the chemical in contact with any metal. Typically, they are decent at suction, but fairly low pressure, maybe 100 psi, but not often that high. Sometimes little tow-behind sprayers for ATVs. So a lot of greenhouses use these little pumps to spray herbicides around the perimeter to keep your perimeter weed free. So they're usually 12 volts, or sometimes they're operated by air pressure in a tractor or a PTO. Essentially, they have a rubber membrane, a flexible rubber membrane that this moves up and down with this offset wheel. And then they have two check valves where the water comes in and goes out. And whoops, I'm really not good at. I'm right-handed, but I'm left-handed, but I write with mouse with my right hand, so it's kind of makes drawing really hard. Anyways, these flapper valves trap the water so it can only go in this direction. So every time that rubber diaphragm pushes down, it squirts the water out, and then when it sucks back up again, it pulls the water in. But because it's a rubber membrane and a plastic housing, it's corrosion resistant. There's a link here if you're curious to see how a diaphragm pump works. There's also hand priming ones where you basically just crank this lever. Some off-grid cottages use these to pump water up for a shower. But more likely you'll see one like this where acids are dosed into irrigation tanks using these diaphragm style pumps. They often click. So the click is the diaphragm moving in or out as it's pumping acid from the bottom into your irrigation tank. So these are actually very common in greenhouses. They're fairly precise. That's what makes them especially good for dosing. Another type of dosing pump is it's actually called a peristaltic pump. Essentially, there's a wheel in here that has little nylon rollers in it, right? And as this thing spins, it squishes this pipe. It squishes it, and that pushes liquid through the pipe, which comes out the other end. If you've looked at the dosatron, or the dose meter that is on the NFT lettuce in the college greenhouse, you'll remember there's little motors that whine every once in a while. Those are peristaltic dosing pumps for dosing A, B, or acid into the lettuce solution. They're very precise, but they're a fairly low volume. They're good for a small system, but for large ones, the peristaltic clicking pumps that I talked about before are more commonly used. Again, because it's not touching the component parts, it's not corrosive. This hose here can be made of like silicone or something that is resistant to chemicals. So you can remove it to clean it or exchange it. So they're very good for dealing with interesting and mixtures of chemicals. There's another picture of one and a link to help you understand how they work. Oftentimes they are put into fertilizer injection systems. So that's where you would see these. Dosatrons. All right, I have a video there for you to look at to help you understand how they work. I think we know enough about these to know that they are present in greenhouses. They are very popular. It's going to be way easier for you to watch the video to learn how they work than for me to try to describe it. Unfortunately, we can't take it apart, but you'll get a pretty good sense of how the pump works when you're watching the video. What I will tell you is pay attention to the video. At the very bottom of the nozzle here, there's a little check valve. And in my experience, it's that check valve that actually causes the most problems when your dosatron stops working. There is wear and tear in the inside of this cylinder from it going up and down, especially if you don't have proper filtration on the inlet side, because sand gets in. And when sand gets in, it starts to corrode and scratch the sides, not corrode, scratch. And then when the piston's going up and down, water is able to leak by and it doesn't work nearly as well. So filtration before water goes into these is really important. And I have made a mess of that picture. Magnetic drives. This is an interesting one. These are typically low pressure applications. The motor is actually sealed and waterproof, and then there's a plastic cartridge with magnets that sits inside and spins, and it's lubricated by water. So these are popular in ponds. In the greenhouse, we see them stirring nutrient solutions to keep them suspended. I've seen them in deep water culture, dropped everywhere to circulate. They are really good for low pressure, fairly high volume applications, and the fact that they're waterproof, there's no bearings, the entire thing is pretty easy to maintain. In fact, you can remove the cartridge and buy another one. They have an impeller on it kind of thing. I'm terrible drawing. You can slide it out and put a new one in, and your pump is back to new again. So they're pretty easy to maintain. We've all seen these submersible pumps. These are like your standard sump pump. Typically, they have a float switch that swings up when the water level gets high, and then that turns the pump on. When it swings back down again, the pump switch is off. You will see these in greenhouses, often in bays that are in sort of tanks or barrels below the surface. The reason why greenhouses put these below the surface is because we're trying to drain the groundwater out from the greenhouse so it stays dry. If your greenhouse is in fairly flat land, like say Leamington, and you get a lot of rain, especially in the spring, that groundwater it doesn't know boundaries, so it will seep into the greenhouse, and the ground underneath your ground cloth in the rows becomes wet. So they bury sump pumps, usually one per house, in barrels, and then those sump pumps pump the water up and out and into a drainage that goes to your irrigation pond. If you are getting wet underneath the plants, typically it means that one of these things is burnt out. Sump pumps don't have a great history for lasting a very long time. It's probably worth checking to make sure they're not running non-stop because they use a fair amount of electricity. Let's say it's in the middle of July, it's hot and dry. You may want to check that your sump pump isn't actually still running dry because first of all, it'll break it or wear it out. It might start a fire, or if nothing else, you're wasting quite a bit of electricity for it to spin for no reason. So keep an eye out for that. Another common location for these is the loading docks where trucks are. We have to pump water out to keep them dry so trucks can back into that lower spot. Typically, these are high volume, low head pressure. So a sump pump is not a good application for irrigation if you're doing a fairly large thing. Now at the college, we use sump pumps to some extent for our hydroponics projects, right? The tomatoes, cucumbers, those are all essentially sump pumps. But those are really small applications. If you had 200 feet long rows, they would not be sufficient. Then there's high pressure pumps. You see these on pressure washers. Sprayers, typically in agriculture, that's what runs the chemicals through. Each one of these represents a piston, and this shaft sort of rotates and moves the pistons in and out, which creates pressure. Here's just sort of one of the more common hydraulic sprayers you'll see in a greenhouse. There's a video link here for you to watch. These things, it's really important to maintain the pumps. Something that I ran into with my farm is I didn't use it enough, and it would start to corrode because water was sitting inside that pump, and it would start corroding. Keep an eye on it. Run it periodically, even if you're not using it that often. There are instructions for some systems to put oil in them so that they don't corrode if you're not going to use it for a long time. Pay attention to that. Another thing to keep an eye out for if you're looking at buying pressure washers is there's two kinds. The first one I showed you is called a triplex pump, where the three pistons are sort of laid out horizontally, right? So there's one piston, two piston, three piston. There's also cheaper pressure washers where the pistons are laid out radially like this. So there's one piston, two pistons, and three pistons. And unlike this one where there's a central rotating axle that moves the pistons in and out, these style have a disc. So basically it's a shaft with a metal disc on the front of it. And the disc is not quite 90 degrees to the axle, which means it wobbles. And as it wobbles, as it rotates, it pushes one piston out, then the next, and then the next, and then it starts again. So it's a wobble plate. We call them axial pumps. These don't usually last very long. That's why they're lower quality. They're easier to manufacture. But for a commercial application, you don't want to buy this because it's going to last you 6 months and then you'll be buying another one. So just beware of that. Cheap Canadian Tire, these kinds of residential pressure washers are typically low-grade wobble plate pumps. I mean, they may last periodically to wash your car, but if you're using it every day, no, it's not going to last long.